Charles, and this is my lab 1 for physics 2 for charged tapes. To introduce this lab, we'll first talk about the purpose, which was first an experimental portion where we applied a charge to a piece of tape and then compared that piece of tape to different objects that we did know the charge of to try to determine what the net charge of the tape was. And then we used experimental and computational models to calculate how much charge is required to make one piece of tape float. To do this, we used Newton's second law, the Coulomb's law, and the gravitational force formula for near-Earth gravity. We came to the conclusion that the net charge for the tape was positive and that the tape requires a charge of 5.167 times 10 to the negative 9th coulombs to make the other tape float. To expand on these formulas a little bit more, the momentum update formula is really important because it helps us calculate the total net force, and net force is critical because we use it to determine that the force of the electrical and the force of the gravitational must cancel each other out in order to have Fnet equal to 0, because when Fnet is equal to 0, that's when the tape is able to float. Here are the initial conditions. The first box on the left shows the given conditions that were given on the instructional sheet, and then the two boxes below are the initial conditions that were on my computational models. The systems and the surroundings remained consistent throughout the lab, where the system was the tape and then the surrounding was the earth, computer, water bottle, my hand, and everything else. And then the procedure I used is listed on the right. First up, for the experimental model, here are a bunch of the questions that were asked in the instructional sheet. You can see here in this video on the left how the tape had an attraction towards my hand, and then I was able to apply a negative charge to the pen by rubbing it against a piece of cloth, and then this is how we were able to determine that the tape had a net positive charge because it would attract to the pen as shown. For part 2 of the experimental, this is a video showing how we were able to make them float. The questions on the left also were asked in the instructional sheet. And then here are my calculations for the questions on the slide prior. The calculations are right here, and then the calculations for the questions on this slide are right here. For this one specifically, we used the surface area of the tape to calculate the amount of atoms, and then we were able to create a ratio for the amount of electrons, from atoms to electrons. For coding, we did two different computational models. The first model was using point charges to demonstrate the two pieces of tape and the forces that applied upon each other, and then the second model uses a line charge to represent the forces applied onto the two pieces of tape. We got different calculations, different charge calculations for both of these, but this was due to the differences in the spread outness of the charges. Model 1 is shown here, where we got the charge required to be 5.176 times 10 to the negative 9th coulombs, which was very similar to the experimental calculation I got, which was 5.167 times 10 to the negative 9th coulombs. And then here's model 2, which shows the line charge that I was talking about, where we got the charge constant of 9.97 times 10 to the negative 9 coulombs. And in order to determine this, it was more of a guess and check method because we just altered the Q until we were able to get a magnitude of the electrical force to equal the magnitude of the gravitational force, making Fnet equal 0. To compare the models, it's listed right here with the 3 different charges that were required to make the tape float. And then for human error, this picture on the left shows what the model would have looked like if I would have used the original 5.176 times 10 to the negative 9th charge, which isn't really accurate because you can see that Fnet represented by the white arrow isn't exactly equal to the left, to the down arrow representing the gravitational force. So that is why we had to edit the Q, but there could have been an error in the guessing and checking method. And then lastly, there could have been an incorrectly estimated distance between the floating tape. For what if, for this question, I would say that nothing would change as far as calculations, because if you invert everything for positive and negative, then it will just continue to cancel out like it did prior. And then for this, the red tape line charge is almost the tape line charge is almost double the amount as the point charge, and I believe this is due to the spacing out of the electrons being condensed as a point charge. For this reason, I think that the 9 times e to the negative 9th value is more accurate because it accounts for the variety and distance of the charges spread out upon the piece of tape rather than just being resembled as a singular point charged. Thank you.